discuss a few applications of determinants and problems. So the four major applications of the determinants are finding the inverse of a matrix A, solving a system of linear equations, then finding the volume of boxes, then P1. So let us consider the first application as solving the system of equations using the Cramer's rule. So Cramer's rule is used to solve linear system of equations followed by the formula xj is equal to determinant of bj divided by determinant of a. So I will explain you the Cramer's rule through an example. So here I have considered an example, that is a system of linear equations like x plus 2y plus 4z is equal to 1, 2x plus 3y minus z is equal to 3, x minus 3z is equal to 2. So here we have to find the unknowns x, y and z. So firstly we have to transform the given system of equations into a matrix equation. So here the matrix equation will be Ax is equal to B, where capital A is the coefficient matrix, capital X is unknown column matrix, see here I have written, and capital B is a column matrix which consists of the elements of the given system, the elements which are present on the RHS of the given system. So this is the matrix B. Okay. So let us find the unknowns one by one. So determinant of A is common to all the unknowns, denominator is same. So let us find determinant of A is equal to determinant of 1, 2, 4, 2, 3, minus 1, 1, 0, minus 3. So let us expand this determinant using the cofactor formula with respect to the first row, so which gives the value as minus 11. Next, the first unknown is x, which is given by determinant of b1 divided by determinant of a. So what is the matrix b1? The matrix b1 is obtained by replacing the first column of the matrix A by the matrix B. Please remember b1, the matrix b1 is obtained by replacing the first column of the matrix A by the matrix B. See, in the first column of A we have 1, 2, 1. So this column will be replaced by the matrix B. B is a column matrix. So other two columns will remain constant. Okay. Divided by determinant of A. Already we have been computed, that is minus 11. Now simplifying the numerator by expanding the determinant, we get the value as 19 by 11. So the next constant we have to find is y. So by Cramer's rule, y is equal to determinant of b2 divided by determinant of a. So what is the matrix b2 here? So matrix b2 is obtained from the coefficient matrix A only by replacing the second column of A by the matrix B. The first and third row, the first and the second column will be constant. So just we have to change the second column by the matrix B to get the matrix B2. Okay. So then we have to get the determinant of B2 divided by determinant of A. So expanding and simplifying, we get minus 2 by 11. And lastly, the unknown Z is given by determinant of B3 divided by determinant of A, where the matrix B3 will be obtained by replacing the third column of A by the matrix B. Okay, so the third column of A by the matrix B, then finding its determinant, which gives the value of determinant B3, and computing we get the value that is minus 1 by 11. So therefore by Cramer's rule, we have the values of unknowns, that is x is equal to 19 by 11, y is equal to minus 2 by 11, and z is equal to minus 1 by 11. So this is one of the application of the determinant where we can solve a system of linear equations. Moving on to the next application where we can compute the inverse of the given matrix through the determinant. So here we have the formula to compute the A inverse, which is the ratio of transpose of cofactor matrix divided by determinant of A. So we know how to find the cofactor matrix of A, okay, divided by determinant A gives A inverse provided the denominator is not 0. So here I have taken an example. Let A be a 2 cross 2 matrix. So determinant, if we have a 2 cross 2 matrix, easily we can find its determinant as well as the cofactor matrix. So without the formula, here we can find the cofactor matrix just by interchanging the principal diagonal elements and multiplying the minus sign to non-diagonal elements. Without the cofactor formula, we can write the cofactor matrix of, that is transpose of cofactor matrix of a 2 cross 2 matrix. Just what we have to do is we need to interchange the elements of the principal diagonal and then we have to multiply the other elements, that is non-diagonal elements, by minus sign, okay, and multiplying this transpose of cofactor matrix by 1 by determinant of A. So that is, we get the A inverse as 1 by AD minus BC times D minus B minus C A. So this is a very simple task, that is finding A inverse of a 2 cross 2 matrix. Otherwise, we have to use the cofactor formula to get the cofactor matrix. So let us consider one more example. In this example, I have taken a 3 cross 3 matrix which is in the form 1 1 1 0 1 1 0 0 1. I can say this is an upper triangular matrix wherein all the elements below the principal diagonals are zeros. So easily we can find its inverse. So firstly, let us find the determinant. So determinant A. So without the expansion, we can write its value. As we know, determinant, if A is equal to an upper triangular matrix or lower triangular matrix, then its determinant is product of pivots. So determinant of A is equal to, here I have expanded this determinant, but we can avoid this as we know the properties of determinants. Therefore the value of this determinant is the product of all the pivotal elements, that is 1 into 1 into 1. Next, let us find the cofactor matrix. So to find the cofactor matrix, we have to follow the sign rule, plus minus plus minus plus minus plus minus plus. Otherwise, we have to use this formula, that is Cij is equal to minus 1 to the power I plus j times determinant of Mij. Determinant of Mij is nothing but determinant of the minor matrix. So here I have written all the cofactors of the elements, okay, and I have taken the transpose of that cofactor matrix, which is again an upper triangular matrix. So therefore, let us write the inverse. A inverse is equal to C transpose divided by determinant A. Since determinant A is 1, therefore A inverse gives the C transpose. I will consider many more examples in the problems while discussing the problems. Let us moving on to the problems. I have solved a few problems from Gilbert's time. So the first problem is, by applying row operations to produce an upper triangular U and compute the determinants of the given matrices. And one more thing we have to find, exchange rows 2 and 4 of the second matrix and recompute the pivots and determinants. So already we have given two matrices of order 4 cross 4 and one more matrix we have to form by exchanging the second and fourth row in the second matrix. So let us consider the first example, where A is equal to 1, 2, minus 2, 0, 2, 3, minus 4, 1, minus 1, minus 2, 0, 2, 0, 2, 5, 3. So before finding its determinant, first let us produce an upper triangular matrix U followed by a set of row transformations. So as we know the property of determinant, that is the only row operations that we will be using is subtracting a multiple of one row from another row, from which the value of the determinant will not change. Okay, subtracting by using some multiple. So, or nothing but the row transformations. So as we know, an upper triangular matrix means all the elements below the principal diagonals are zeros. So this is a 4 cross 4 matrix. So we need to make all the elements below the principal diagonal to zeros. Okay, which are the elements below the pivotal elements? Here either we can exchange the rows, that possibility is there. So when we exchange the rows, the determinant changes, the value of the determinant gives by changing its sign, so that we can count how many times we exchange the rows, that many times we need to multiply by minus sign. So here I have marked the elements which are all will be zeros. Okay, these elements we need to make to zeros through the set of row transformations. Okay, so easily we can make out the elements. So as we know, first, because already all of you have know about the row transformations, so here already we have one, so easily we can make this entry, already this is 0, so only these two entries we need to make to zeros through the row operations, that is R2 is equal to R2 minus 2R1 and R3 is equal to R3 plus R1, right? So the first operation I'm using is R2 is equal to, or R2 changes to R2 minus 2R1. Now I will get the new row with new elements. The other rows we have to keep it as constants. Okay. See, by employing this row transformation, R2 minus 2R1, I'll be getting a new row as 0 minus 1 0 1. Okay, see, 2 minus 2 0, 3 minus 4 minus 1, minus 4 plus 4 0, 1 minus 0 is 1. Similarly, let us change the third row. Okay, by making this entry to 0, the set of operation is R3 plus R1, because we have minus sign here, so I will get the equivalent matrix as, see, first row constant, second row constant, fourth row constant. I'm just changing the third row, so I'll be getting a new row as minus 1 plus 1 0, minus 2 plus 2 0, 0 minus 2 minus 2, 2 plus 0, that is 2. Okay, next observe again the elements below the principal diagonal. This entry and this entry we need to make it to zeros, right? Okay, first let us make this entry to 0 with the help of second row. This is only the possibility. Here we cannot use the first row or the third row, only we can use as the second row, right? So here the set of operation is R4 changes to R4 plus 2 times of R2. Isn't it? Easily we can identify the scalar. So here we have to, so if you multiply the second row by 2 and if we add with fourth row, then easily we can make this element to 0. So this is how we have to consider the set of row transformations. Then the fourth row will changes to, keeping the first three rows as it is, the fourth row changes to 0, 0, 5, 5. So finally, one entry I need to make to 0, which is 5, with the help of the third row. That is only the possibility, right? I cannot use the first row or the second row. So this will be 0 with the help of the third row. So let us choose the scalar. So here I have -2, here I have 5. So what multiple I have to choose so that this entry will be 0? So if I multiply the third row by 5 by 2, okay, then subtracting with fourth row, then this element will be 0. So here a set of operation is R4 changes to R4 plus 5 by 2 times of R3. Then I'll get an equivalent matrix as, so write down the first three rows as it is. The fourth row will changes to 0, 0, 0, 10. So now observe all the elements below the principal diagonal. So all the elements are zeros. I will show you. See, all the elements below the principal diagonal are zeros. So therefore, the given matrix will be reduced to an upper triangular matrix. So through the set of row transformation. Now let us find its determinant. To find its determinant, here we have to apply the rules of determinant. So we have applied a set of row transformation in which subtracting a multiple of one row from another row, which doesn't change the value of the determinant. So therefore, determinant of A is equal to determinant of U, which is equal to product of all the pivotal elements. That is product of all the diagonal entries. So that is equal to 1 into -1 into -2 into 10, that is 20. So here, by reducing, because it is mentioned like find the determinant of the given matrix by reducing into A. So here we have to use a set of row transformation to reducing A to U. Then we have to get its determinant. Once if it is reduced to U, then we can write its determinant as the product of all the pivotal elements. Moving on to the next sub-example. We have given the second matrix B as 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 minus 2. So in this matrix also we have to reduce the matrix B to matrix that is upper triangular matrix. So let us use a set of row transformation. The first and foremost is we can exchange the rows. Number of rows we can exchange. So how many times we exchange the rows, that many times we will get the negative sign while finding its determinants that we have to count. That is the property of determinant. Okay. So here I have changed the I have exchanged the rows 3 times. Okay, R1 to R2, R2 to R3, R3 to R4. So at the end, while finding the determinant, I have to multiply that determinant by 3 negative signs. That is -1 to the power 3. I have to consider because according to the property of determinants. Then using the another property wherein the value of the determinant remains unchanged. Okay, that is only these 2 entries after applying a set of row transformation, that is exchanging of rows. Okay, the matrix will be reduced to this. Okay, in which only the 2 entries I'll have to make it to zeros. That is 2 and -1. Right. So here the row transformation I have to apply for only the 4th row. Right. So first let us make this entry to 0. Next let us make this entry to 0. So here the set of row transformations are. So easily you can identify the set of row transformations, right? Just by observing the elements. So in R4 I have to, so in R1 it is -1, isn't it? So the possibility is only the first row, right? So R4 plus 2 times of R1 gives this entry to 0. This entry will become 0. and other elements will changes to 3 minus 2 0. And the next further I got one more element over here. Okay, so now these two entry I have to make to zeros. So let us use a set of row transformation, and finally I'll get an upper triangular matrix U. So B is reduced to U. Therefore, the determinant of B is equal to determinant of U. Okay, so let us count the set of row transformation. In the set of row transformation, 3 times I have exchanged the rows. So the determinant of U will be multiplied with 3 negative signs. So minus 1 to the power minus 3 times all the product of pivotal elements. Minus 1 into minus 1 into minus 1 into minus 11, which gives the value as minus 11. And the last sub example is, so produce the upper triangular matrix U from B by exchanging second and fourth row. Okay, so this problem is similar to the above problems. So this is same as above. Again, we have to use a set of row transformations to reduce the matrix to U. Okay, then employing the property determinant of B is equal to 2 times. While applying the row transformation, we have used the row transformation, that is exchange of rows, where determinant of U will be multiplied by minus 1 power 2, because so if the rows will be exchanged, then determinant changes with signs. So minus 1 power 2 times determinant of U, which gives the value 11.